So is my screen visible, and am I audible, everyone? Am I audible to everyone? Okay. So good afternoon, everyone. Good afternoon, everyone. I am Adnan Khan, and I am currently pursuing PhD from IIT Delhi. And today is the second problem-solving session for the course Design of the Power Electronic Converters. And like this problem solving session we shall be carrying on every Sunday from 3 to 5, like and today's is the second problem solving session. And this course is being taught by Professor Shabrinath. And like in the previous week, as I told you, I shall be going briefly through what had been taught in this week, and then we shall move towards some problems that will help you in this week's assignment. And we shall see some of the problems, uh, how to tackle them, and how to, like, this course is mainly about the design of power electronic converters. So basically this week as well, some aspects had been discussed which will help you how to, like, choose different components for the converter topology. If you have certain voltage or current ratings, how to like choose the components for those things. So coming to this week, what had been taught in this week, like in the previous week, what discussed about the applications of this power electronics. Then what had been taught is, like, we saw two converters. One was the buck and other was the half bridge, H bridge, full bridge type converter and inverter. Then some problems we saw at how to design the boost converter, and there was some assignment on the buck boost as well. So in this week, in the previous week, I told you, like, all the analysis what that had been done were pertaining to the ideal switches. So our switches were ideal, and we did all our analysis of the converter topologies, keeping in mind that our switches are ideal. But today in this week, what had been taught is, like, what is the difference between an ideal switch and a non-ideal switch. So what are their characteristics, like what to keep in mind or what to take into the consideration for the non-ideal switch. We shall differentiate between them. Like, I shall give a brief overview. This has been taught by Professor Shabrinath in detail in this week. Like, you can go through those lectures as well as the transcripts here. here I shall here I shall discuss briefly about the difference between the ideal and the non-ideal switches. Then what had been discussed about is, like, diode characteristics, and mainly in this week it was pertaining about, like, how to see the data sheet of diodes or MOSFETs. Like, if we have a diode and we have a certain part number, and if we if you shall, like, type or search for that part number, you will get a data sheet, and there will be a multiple characteristics associated with that diode, like its part number, its voltage blocking capability, current carrying capability, and some other aspects that we will see in the subsequent slides. And in a similar fashion, like, we could see what had been taught in this week was about the MOSFET. Like, what are the different characteristics of the MOSFETs, what are the different attributes in terms of the designs, how to see the data sheets, how different characteristics of the MOSFETs, be it the voltage current levels, or like input capacitance, output capacitance, like junction resistances, and etc., that we'll subsequently see in the subsequent slides. That was the main things that had been discussed, and I think one of the and what is the problem that has been given in this week is you have been given some questions, some data sheet of some of the component, and you have to go through that data sheet, and there have been certain questions that have been asked pertaining to that component, and you have to answer those questions. The main thing is you should be able to uh, if you are having some what should I say, if you have a a topology, and if you want to design some component, choose a switch or a diode for that thing, and if you have the ratings that are given to you, then how you shall choose how you shall choose a particular component, and these lectures were mainly pertaining to that and to help you with that thing. So so coming to the first thing that have been discussed is like ideal difference between the ideal and the non-ideal switches. So in the previous week, like what we had seen is we did all the calculations and analysis based on the non-ideal switches, and if you have had the idea of the elementary courses of this power electronics, there this thing we cover like what's an ideal switch. Like an ideal switch is like it should be able to block the infinite voltage. Like during the off stage, this switch, it can be anything. A switch, it can be a diode, it can be an IGBT, it can be a BJT, it can be a MOSFET or anything. So an ideal switch should be able to, when it is in the off stage, so when it is in the off stage, it should be able to block the infinite amount of the voltage across through it. That is the ideal, that is the first characteristics of an ideal switch. And but we know that a particular switch, be it a diode, be it a MOSFET, be it an IGBT, won't be able to block infinite amount of the voltage across through it. Every component, every switch will have its own characteristics and own amount of the voltage that it shall block. So a non-ideal switch will have a finite blocking voltage capability. Like some of the switches will have a 100 volt. We have some MOSFETs, they have 600 volt, some 900 volt MOSFETs, like we have 1.2 kV. When we go for the higher, like we have an IGBTs of higher, like 1.6 1.7 kV IGBTs. Then we have some GTOs which have a voltage blocking capabilities of SCR, and GTOs we have a voltage blocking capacities of in kilovolts. So a non-ideal switch will have a finite blocking capability, but ideally any switch should be able to block infinite amount of the voltage across through it in an off state. And when we turn on our switch, what should happen is it should be able to carry or conduct an infinite current in the on stage. So but this characteristic is not possible for a non-ideal switch, because each switch will have a certain current carrying capability in its own stage. So we will be having a different switches for different applications, for different current ratings, and there will be different applications and different current ratings. We'll be having the switches for signal levels that have to that will have a small current carrying capability. Some switches will be having low voltage blocking capability, but they will be having a high current carrying capabilities. So some switches will have a medium current carrying capability of 60 amps, 63 amps, 100 amps. Some of the devices are able to are able to conduct or carry the current in kiloamps as well. So here is what that non-ideal switch will have a finite amount of current carrying capability. And also what is the for the ideal switch, ideal should be able to carry the infinite amount of the current in the on stage. Also, as we know, as we'll see in the diode characteristics, the ideal switch should be able to, like, we should not have any like on state voltage drop whenever this switch conducts. But we see there is some parasitic resistance associated with the devices. We have some on-state voltage drop associated with our switches. That is then this is like a in the non-ideal we have some finite on-state drop whenever the switch conducts. But in ideal case there should be no voltage drop associated in the on state with the switch. In a similar case, when our switch is in the off state, there should be no current that should flow through the device. But that is not happening in an actual device. In an actual device, there is some leakage current that flows, even if that current that is very small in the microamps. Microamps, but as such, like in the non-ideal case, there is some small leakage current associated in the off state as well. In the ideal state, there should be no leakage current as well. Coming to the other characteristic of an ideal, ideally our switch should be able to carry the current in the both directions, in the positive as well as the negative direction. As soon as we shall close this switch, if you can see here near my arrow where it is pointing, as soon as I shall close the switch, it should be able to carry the current, the whole current, in any of the direction, be it positive or negative, forward or backward. But that is not possible with the actual switch. Let us say we have a switch that is a diode. Here it will be only able to conduct the current in the positive direction, in only one direction. If we have some other switches like IGBT, MOSFETs, IGBT is able to carry the current in the forward direction. If you have to carry the the reverse current, what we do is we have a anti-parallel diode associated with the IGBT, as you might have seen. Similarly with the MOSFETs are able to carry the current in the negative direction because of an inherent body diode as well as through the channel. But what we usually say, MOSFET usually carry the current in the one direction. If we have the full carrying capability in the reverse as well, that we should have an anti-parallel diode. The thing I want to tell here is, most of the devices, they carry current in the one direction, but ideally our switch should be able to carry the current in both directions, in the forward as well as the reverse direction, and there shouldn't be any voltage drops associated in the on state. And in the voltage blocking state, our device should have the capability of withstanding both positive as well as the negative voltage in the state, ideally. But that is not possible, as that is not being seen in most of the devices. If we see most of the devices are like unipolar devices, and they are able to block only a particular voltage. If we take a diode, it will block the reverse voltage when it is in the reverse biased mode. If you have a MOSFET, it will block the forward voltage up to a threshold until we will give a gate pulse to it. Till then it blocks a certain forward, it is in the forward blocking mode, and so for the IGBTs, BJTs, and etc. This was about like between difference between the ideal as well as ideal and non-ideal switches. The other thing is like, ideally, when we turn on the device, what should happen is our switch should instantly turn on from the off one state to another state. Let us say my switch is in the off state. It is not carrying any current. As soon as I am turning on the switch, it should instantly turn on. There should not be, but what we see is there is some delay associated. There is some delay because like actually what would happen is our device won't instantly turn on. It will take some time before it is turning on from the like if we in terms of like from 0 to 1, that 0 is an off state and 1 is the conducting state. There is some delay associated with it, and during that portion what happens is our like blocking voltage comes to 0 and current will start rising till it is able to carry the whole current. And during that time there are some switching losses associated with the device that are categorized under the switching losses. So what we see like there is some time that a device takes to turn on from one state to another state. But ideally what should happen is, like this transition from one state to another state should be instantly without having any delay. So these are some of the differences that are between the ideal. So you can see like most of the devices are non-ideal, ideal in our day-to-day life. Like what we every time what we want when we choose a device, we should see like these on-state drops should be minimal. We should keep in the mind whenever we choose some of the components or design a certain choose a certain device for a certain topology. Like we should see what are our parameters and we should try to minimize these things like on-state drop, turn on time, and etc. The better. Or sometimes we may have some applications, we shall see like it may depend upon the parameters as well. Coming to the first, like then after this what had been taught is like different types of diodes that were discussed in this. Like first were like the simple standard diodes that are there, and there are some other types of diodes that were discussed, like Schottky diode and fast recovery diode. Before going to that, like let us first see uh, about the standard diode. As we know, diode is nothing but a p-n junction. We have a like a p-type we have a semiconductor device where we have a p-type where the majority which has been doped with a trivalent, where we have like a we have like a positive charge due to holes, and we have an n-type semiconductor which has been doped with the pentavalent impurity. When they are being brought together, we have a p-n junction. A junction is formed there. You would have you have read about that junction potential will be having, there is a barrier is formed, and then there is a biasing. If we forward bias, it will start conducting. If we in the reverse bias mode, it will it is like diode is in the off state. Like there is some leakage current, but the diode is usually what we consider is in the off state. So here if you can see and these diodes are of like different voltage ratings. They are able to have, we have a power diodes like they have very high voltage blocking capabilities in, they can go up to in like kilovolts as well. Besides they are able to like carry high current. Let us take a circuit, talk about a circuit. If you can see here, we have a rectifier, and this rectifier, we have an AC voltage source between the two legs of the rectifier, and here at the output we have a load. So if you can see the waveform here, if we have a like a 50 hertz 50 hertz AC source, so we know that these diagonal switches will be turned on for the positive interval, and these will be turned on for the negative interval. So our diodes will be off for the half the cycle and on for the half cycle. For the cycle, like when our diodes are turned off, it shall block this negative voltage VD. If you can see, that will be a sinusoidal voltage that will be across it, and it has to it will be turned off for the half cycle, that is 10 millicycle. And if you can see, we don't have to in the rectifier circuit, we don't have to switch these diodes very fastly. Like it has to turn on once in every fundamental cycle. And when these are on, like if we have a like very high inductive load, we can assume that the current is constant. Like we can see there will be a square wave current that will shall flow, and you can see when the diodes are on, it has to carry this current ID. When it's off, like it will block this voltage. If in this like a rectifier circuit, we don't have to switch. We don't have to like switch very fast. Like in one fundamental circuit, like once cycle, once they have to turn off or on. So we can use a simple standard rectifier and diodes here, and there is some reverse. When these diodes turn off, they don't instantly turn off from some current to zero, because like if you go through the physics of it, there are some while turning off, the overall current in the diodes is through the majority and the minority carriers. As soon as our current goes to zero, there are some minority carriers like which have to like recombine with the positive charge, and because of that there is some reverse recovery current associated with this. And if you go through the physics of this diode, you shall get to know about that thing. uh, because of this, like the standard diodes have a high reverse recovery. So this was about the standard diodes. Now the other types of diodes that have been discussed in this week were like the Schottky diodes. And what is like different from the Schottky diodes, like the reverse recovery of the Schottky diodes is very much small. We can say it is almost negligible compared to the standard diodes. And where are these like Schottky diodes used? These are used under the application where we have to switch at very higher frequencies. Let us take an example here. If you can see a circuit here, buck converter circuit here, we are switching this circuit at the 50 kilohertz. What we saw earlier is like we had the rectifier circuit, and our devices are getting turned on and off at once in one cycle, like in the 50 hertz frequency. Here we are turning on off our devices at 100 kilohertz. We are turning on these devices at 100 kilohertz, and if we are having a very high reverse recovery, there will be a lot of losses that will be associated with these components. So what we want here is we want our devices to have the very low reverse recovery losses. So here what we can see is what we use is like Schottky diodes can be used, and these Schottky diodes usually are not rated to very high voltages, but they are able to like carry the high currents. If you can see in the off, when this is in the off, it will block like V in voltage, like this diode, and when this diode is turned on, it shall carry this inductor current, like this current. And you can see like this device is turned once in 10 microseconds. That's it. It has like a switching frequency of 100 kilohertz. There is other like a type of diode, what we say is fast recovery diode. These diodes are between the standard diodes and the Schottky diodes. These diodes, fast recovery diodes, as you can say, as you can see from the name itself, they are called fast recovery diodes. They are able to have a fast reverse recovery, but they have a reverse recovery that is greater than the Schottky diode but lesser than this standard diodes. As such, like they can be used in the topologies where we have intermediate frequency level like of 10 kilohertz inverters with 10 kilo, 20 or 50 kilohertz. The higher we move in the frequency ranges, we want our devices to turn on and off, have very small or next to like zero reverse recoveries, and also should be able to turn and on off very fast. The next thing that was being taught is about like the diode characteristics. As I had earlier discussed, if you can see the diode, it's made of a p-n junction, and you can see we have an anode part, p and n, and we have a anode, and p side is an anode and k is a cathode. What happens is like, what is the first like thing when we have when I told you like when this p and n are junctions are brought together, there is some barrier potential that has been developed in the depletion. Okay, about the fast recovery diode, someone is telling me to repeat it. About the fast recovery diode, these are intermediate. They have like we have a standard diode, they have some reverse recovery. Then at one extreme, and if you can see, there are we have a like standard diodes, they have a very high reverse recovery time, and Schottky diodes on the other hand have next to none or very small reverse recovery. And these fast recovery diodes, they are intermediate between the Schottky diodes and the standard diodes. Like these diodes we can use in the applications where we have an intermediate frequency operations like 10 kilohertz, 20 kilohertz, so and so forth. The higher we move in the frequency spectrum, like in the operating range of the converters, we want our devices which will have a very minimal or zero around like this reverse recovery. So coming to the about the characteristics of this diode, like this is a common for every all the diodes, like they'll follow a typical pattern. If you can see, we have a I have a picture of the diode here where we have a p and n, where it is denoted by A is anode and K is cathode. When we if you if you can recall about the p-n junctions, whenever like p and n are brought together, there is some barrier potential that has been developed between the p and n. And if you now take a p-n junction diode and we'll apply a certain bias across it, we can have it in a forward bias mode or in the reverse bias mode. Now in the forward bias mode, if you see, when we have a certain voltage, zero voltage applied across it, it won't start conducting. Then if we try to increase the voltage small, like for first 0.1 volt, you will still see there is no conduction through the diode. That diode still has not conducted until like our diode won't start conducting until it will reach the threshold. The threshold is a voltage like where our barrier potential, where this voltage is able to overcome the barrier potential and our device starts to conduct. Like for the silicon, you can see it is like 0.7 volts, or you can see for the germanium it is like 0.3 volt around. So we have a threshold voltage, and till this voltage, like our diode is mostly off, like there is some current that will flow, but our diode is not in the conduction mode. But as soon as we have the voltage that is higher than this threshold voltage, our if you can see, the as soon as this forward voltage is higher than this threshold, the device will start conducting, and it will follow the linear line. It is in the linear region, if you can see. That means as we increase our voltage, the current will increase. And if you can see, if you can linearize, have an approximate this with this, we have a VD and ID, and the ratio of this will give us the equivalent resistance of this diode. If you can apply a Ohm's law, we can assume that this is a linear. If you can see, that has been given by this equivalent resistance, and if we take the ratio of that, that is the Ohm's law, like we can have the equivalent resistance of this diode. The other thing, the other aspect aspect or characteristic of the diode is the blocking voltage capability. What we know is, whenever we this was about the forward conduction, when we forward voltage or the diode is forward biased. But what happens is, when the diode is reverse biased, so when we apply a negative voltage across this diode is able to block that voltage. But this diode is able to block this voltage up to a certain volt limit. After that, what happens is, as everyone knows or has read in your earlier classes in your 12th and maybe some of you are doing in BTech, have learned that after that, breakdown of that happens, and of the diode happens. So the voltage that this diode or the device is able to withstand before the breakdown is called the blocking voltage. And in this blocking voltage blocking area, what happens is, the device is able to block this negative voltage, and no current flows. Only a small amount of the current, that is the leakage current, that will flow during that period. That is if you can see, that is a very small amount of the current that will flow. So you can see, our device should be able to we should operate our devices in the region where it should be able to withstand this amount of blocking voltage in our topology or any circuitry. And there is, if you see the data sheet of any of the device, what you'll see is there is a limit, or it has been given the amount of the current that a device will be able to conduct. So we should operate our devices between those things. So this was about the characteristics. Now we'll see, this were about the VI characteristics of the diode. Now we'll go about the switching. What happens when we turn on the switch? So as soon as a device turns on, before that, what was that, device was blocking of some voltage. If you can see here, that is VR, reverse voltage, it was blocking. Now now I want to turn on my device. As soon as I want to turn on my device, what should the amount of the voltage it is blocking, it will decrease. Now my voltage will become 0 and my current will start to rise. So if you can see here, that my current is rising from 0 to some forward current value IF, to some peak value, and this current will rise by some slope that is given by DIF by dt. And these are the characteristics of a particular device. If you go to the data sheet, this data is given, what is the rate of rise of the current, at what di by dt our current will rise. That is different for the different devices. Similarly, you can see our this VD it will turn on, our this voltage from this reverse voltage will come to this 0. Mostly you can see this there is some T1 is the time associated when our voltage from reverse from some blocking voltage will have some oscillations that will be associated with the parastix or the reverse recovery, forward recovery. If we are in the during the turn off we say reverse recovery, and during the turn on say forward recovery. Because of that, that will be T1, and after that it settles and comes to 0. That is the time T2, and this is given by the turn on time T1. Turn on time is given by this two intervals T1 plus T2. Usually you will see this thing is not given in the data sheet. This is because the turn on time of the devices is very small compared to the turn off time. As such, we usually neglect this. We don't pay much attention to the turn on characteristics as compared to the turn off characteristics. Now these are now coming to the turn off characteristics, as I was earlier telling about. During the before the device is getting turned off, there about the diode, before it is getting turned off, it is carrying some current. Let it be some like a peak current here. If you can see some this current it is carrying at this point. Now we want our devices, like if we take a rectifier circuitry, we have after a half cycle, if we have a highly inductive load. Now our after the half cycle, our devices now have to will turn off. Now the current has to shift from one device to another device. What will happen? The current in one of the devices will start decreasing. It will decrease by the rate we have di by dt that is given in our data sheets. So our current will decrease and come to the 0. Now what will happen? The current won't instantly go to the 0, and there is the port time from the steady state current coming to the 0. It is given by the T3 current, and after that there is some T4, during which what happens is reverse. This is the reverse current due to the minority carriers that are across the junction. That is you have to, for this to understand this perfectly, you go to the device physics, what happens in the diode. So these minority carriers, they will recombine till this peak point. After that what will happen, it will go to some reverse peak current here, and after them that current will come back to 0 in the T5 interval. So during, you can see from T4 to T5 there the current goes from 0 to some reverse peak current and comes back to 0. This is called the reverse recovery current, peak of the reverse recovery current. As soon as my current goes to the reverse peak, now my voltage will start to build up from 0 to some voltage block. It has to block some voltage. It will build up to that thing, and the charge associated with this reverse recovery, we call that reverse recovery charge. And there is one factor that is associated with this reverse recovery. We call that as the softness factor, and that is the ratio of the T5 to T4. This is how softly our device will turn off in the reverse recovery. If we have reverse recovery, usually you will see this T5 and T4 are 1, and that will have, we call that as a soft reverse recovery. And if this TF is smaller than T4, that softness factor is then very less compared to that thing. And also earlier I told you that this T off time associated with the turning off is very high compared to the turn on. As such, the losses that will be associated with the turn off losses are high compared to the turn on. As such, if you can see in the data sheets, mostly the data is given for the turn off rather than the turn on. The other attributes, the characteristics that were uh, seen, like if you have a data sheet of a component, what are the different things that are being given. You can see we have a first thing that is given is the voltage rating of a diode. We have a if you can go through the data sheet of this diode, you'll see in the voltage ratings there will be different voltage, like we have the reverse voltage, uh, then we have the repetitive peaks and non-repetitive peaks. If you can see like we are a maximum repetitive peak reverse voltage that is being given is it is around like 50 volts for voltage code like this. And these is the repetitive voltage, is the repetition of the voltages that we can apply across these devices without these devices getting damaged. And what is the like non-repetitive voltage, like but this doesn't mean like our device will be able to handle only this amount of the voltage of the 50 volts. It can handle higher than that, but we cannot give that voltage repetitively to that device because it can damage then devices. So what is the non-repetitive voltage that we can across that device? That is a non-repetitive peak voltage that we can give, and that is then we can give a 75 volts for a 50 volt device, and for like 100 we can go up to like 150 volts. That means if we have a pulsed voltage that can go up to, for the 50 volt device, it can go up to like 75 volts without damaging or harming the device. But we cannot repetitively give this high voltage to the device. The other aspect was about, like, this is the for blocking voltage that we saw, like about the diode we see the reverse blocking. Now the what is the in the blocking region, what is the reverse leakage current that is that flows through these diodes? What is the leakage current in the blocking region? If you can see, we have that if you can look at the data sheet, this data is given here for certain parameters. If you can see here, for certain parameters, like if you have a junction temperature of a 150 degree and reverse voltage of 45 volts, like what is like the current that shall flow, that minimum it will be like 650 milliamps, maximum like 1000 amps. Like then there are some other there are multiple data that is given. If we have a junction temperature of 25 degree and now we are at the rated voltage, that is the rated voltage of these devices, then it shall have the reverse leakage of 0.3 milliamps, and so and so forth at 125. Also there, if you can see, some of the graphs are also provided with the data sheet. If you can see that one of the graphs that is with reverse recovery reverse current with the reverse voltage for different temperatures. First thing what you can notice here is, as we will increase the reverse voltage across a device, you can see the reverse current is for increasing for a particular temperature. Also, the other thing you can notice here from the graph is for different temperatures, if we have a constant reverse recovery but we have a different temperatures, let us say our reverse voltage is at, like, let us say 25 volts. You can see for 25 degree centigrade, like the current is like below 0.1 milliamps. For 50 it is higher. For 75, that means like with the increase in the temperature, our reverse current also varies, like it increases for the same voltage, reverse blocking voltage. These things you can interpret uh, these things you can interpret uh, in the data sheets. The other thing, this was about the reverse blocking state. Now we can see about the conducting state of the diode. So in the conducting state, what happens is, in the forward conducting state, we have the amount of the current that our devices is able to carry. So here you can see we have a our devices is this what will be able to have some of the average current that it can carry. Then we can have a peak current, some peak current that can flow through our devices, that will be in a repetitive fashion, not in the continuous way. And there will be some other data that will be given is some non-repetitive peak current can flow through our device. If you can see for this diode, you can see the average current that can flow is around 80 amps at 72 degrees. But for the same devices, if you can see, we have a repetitive current like a square wave of like 20 kilohertz. At 20 kilohertz frequency, we can go up to a current of 160 amps. Still our devices won't get damaged. Now it is up to us, you have to see what are your uh, what can I say is specifications you want a particular component for, and you have to look for these things if I have to carry certain amount of current, then I have to look for these. Is my device able to carry that amount of current? If I have a repetitive current of some frequency, will my device be able to handle that amount of current? You can see here our device is able to handle a repetitive current of 160 amps, but on average it shall be able to carry only the average of 80 amps. Why so? Because if ultimately it is about heating of the devices, because as soon as more average current will flow through the devices, more losses, there will be some more on state drop and losses will be associated with it, and subsequently the temperature devices will rise up and it can damage the devices. So this is working parameters given to us, in these parameters our devices won't get damaged. And also our device can handle and up to, if you can see the data sheet of this device, it can be handled some peak surge of up to 800 amps as well without getting damaged. But this amount of high current shouldn't flow through the device for the long period of the time, because then there will be a lot of heat generation, and that can eventually damage our device. This was about a forward conducting, and you can see in the forward conduction mode there will be some forward voltage drop associated with the devices. You can see, if you can see here in the bottom, forward this data is usually given with every data sheet of a particular component. Like we have a forward voltage drop of a diode, if we have there are conditions associated with this. So it is given, if we have a 50 amps current that is flowing and we have a 25 degree, then what is the typical forward voltage drop? That is, the typical forward voltage drop is 0.54 volts, and maximum it can go up to 0.58 volt. If you can see here, there are certain three of the graphs for three different voltages, like junction temperature of 25, 125 and 150. If you can see, there is an at 25 there is some first a threshold voltage of around, if you can see, 0.15 volts around, and then after that there is some on state voltage drop uh, particular to current that is flowing through the device, and it is given for 100 amps. If we have a 25 degree centigrade, then we have a particular on state voltage drop of 0.69 volts. That can be also verified. Forward current is here at, if you can see, this is in the logarithmic scale. You can cross check with these what is given in the table with this device, and it will follow exactly that thing. And for that, if you can see, for the at higher temperature like of 150 volts at similar currents, you can see that on state voltage drop decreases. Like we have a like 0.48 now for 150 degrees centigrade. And if you can see, like these curves are like parabolic look to you, parabolic, because this is in the logarithmic scale, otherwise it is in this like a linear scale. Also, like you can get the forward slope resistance, as I had discussed in the previous slides. Like we have you can take two voltages and currents, like you can divide them and get the slope, and that will give you the resistance. This was about the other thing that is also given in the data sheet, is about the reverse recovery. Information that is given is about the reverse recovery. Like I told you, mainly when we turn off, like we'll be having some current that will be flowing through the devices. Then that current shall decrease from that steady state value at at some rate, and it will first go to zero. Then there will be some reverse recovery. This current will go to some reverse peak current in the time TA, and then there will be some current, some time TB current, and total of this TA and TB is the reverse recovery time. If you can see the data sheet, if you can see the data sheet here, that TRR is given this gives us the total reverse recovery time, TRR, reverse recovery time. And there are certain parameters that these time will be correct only for these parameters. If we have a like a for IF of like 1 amps, and di by dt will be of 100 amps per microsecond, and if you have a VCC of 390, and at the temperature is also given, then we have a like reverse recovery, minimum reverse recovery, or typical minimum reverse recovery of 46 nanoseconds, and maximum it can be around like 75 nanoseconds. Similarly, for other parameters like 80 amps, that is given here at 25 and 127 degrees, we can have like 74 nanoseconds and 219. You can see the reverse recovery increased with the increase in the like steady state value of the current, because if we had the 1 amps, we had around a reverse recovery of 46 nanoseconds. Now with 80 amps, with the similar of VCC like voltage, we have like an increase in the reverse recovery. That means our reverse recovery will increase with the increase in the steady state value of the current that is flowing through across the device. Also, you can see like the other things that are given in the datasheet, or it is given like TA is given, TB are also given. What is the total charge, reverse recovery charge, that's also given in the datasheets for a particular for the particular specifications. Also, there will be some graphs through which like you can see the reverse recovery current, peak of the reverse recovery current if you have di by dt, what it shall go like for IF. Like if you can see first graph, di by dt is given at a particular temperature, you can calculate what is the reverse recovery current at that time. Also, you can have you can see the reverse recovery charge for different temperatures at different di by dt's for particular current, because like usually maybe you have to see the particular reverse recovery current for your case. Let us say it is not like 80 amps and 1 amps, then you have to curve fit the things and calculate as per your specifications, because the every data won't be given in the data sheet. So by properly seeing these data sheets and these graphs, you can calculate these things. So this was about the reverse recovery. Now the other thing, the other important thing is like the thermal characteristics of this of the diode, or you can say any device. So if you can see, we have a device here. So if you can see, this yellow thing is our devices. What we call it is like, let us say if we have a diode, we have a PN junction there, or if we have a MOSFET, we have a die. Can you, Mayur, can you please like turn off your mic? So we have our junction here. So at the device level we have a die, and there that is mostly our devices, and you can see like there what we call at that thing is the junction. After that junction there will be some casing around that devices, die of that devices, that we call as the case. And after that there will be after that what we do is we mount that device over some heat sink, so that we shall be able to dissipate that amount of energy. And then we have some heat sink over which that device is mounted, because like this the amount of heat that is being generated by the device, we should be able to dissipate that amount of heat. So usually in the thermal characteristics, what is kept in mind is, we saw like there are some losses associated with our devices, be it our diodes, MOSFETs, or anything. During our switching there will be some losses, during our conduction there will be some loss associated with this. Ultimately what we have to keep in mind, the amount of the power that has been lost or dissipate, we have to dissipate that amount of power, otherwise there will be a rise in the temperature. And if you can see here, these thermal circuitry is analogous to our, if you can see an electric circuit, let us take this as this junction. At this junction there will be some junction temperature, and between this junction and the case there will be some thermal resistance between these two things, and this thing is provided in this data sheet. And the amount of heat that will flow from the junction to this casing will be determined by this thermal resistance. Usually like this is like joule per Kelvin, or Kelvin per watt. It is giving what is the thermal resistance between this junction and this casing. Lower this thermal resistance, that means it higher the ability to dissipate this amount of the heat. After that there will be some temperature rise at the casing, and between this casing and the heat sink, this heat sink material will have its own thermal resistance. And we have to keep in the mind that this thermal we have to choose this heat sink in such a way that heat sink will have a thermal resistance. There will be a thermal resistance between this case and this sink, and this resistance is also given in the data sheet between this sink and this case, because like this cases thermal resistance will determine the amount of heat that will transfer or get dissipated. And after that we have a heat sink material, and the thermal resistance of that will be given by this heat sink material. It will be provided not in the device data sheet but in the thermal interface or heat sinks data sheet. And it shall we have to keep in mind the amount of the power that will power loss in the device. Our thermal heat sink material should be chosen in such a way so it should be able to dissipate all that amount of heat. And after that there will be an ambient temperature. You can see there are like different temperatures here. Junction temperature Tc is the case temperature, then this is the like a source temperature, and then we can have an ambient temperature. So between all these there will be some thermal resistances between them, and these informations between junction and case, that will be provided in, and between case and this sink, that will be provided in the data sheet, and between like this and ambient will be like if you have our the ambient of a room, or if you have it air or air cooled, that will be the ambient temperature. Ambient temperature that will be determined by this heat sink. If you can see for like for this diode, it has been giving that maximum junction temperature and temperature range Tj, it can be varied from like -55 to 150 degrees, huh? So, or also it is giving maximum thermal resistance between junction to case, it is given RTJC, that is giving, it is between like 1.4 to Kelvin per watt. That means if a 1 watt is dissipated between will flow from this uh, from junction to the case, there is a rise in 1.42 degree centigrade or Kelvin. It is approximately almost same, and this is the maximum limit. Also, if we have like a heat sink, then from case to heat sink, it is giving case to sink, it is giving like 0.2 Kelvin per watt. That means for 1 watt of energy, like there will be a rise of 0.2 degrees. And after that we have to look what will be the amount of energy that will be dissipated, what is are the losses associated with our devices, and if we dissipate all the amount of energy, what is the rise in the temperature, is it below this junction temperature, should not exceed our working range, otherwise that can damage our devices. Then we have to choose our heat sinks in such a way, like be it water cooled or provide some fans associated with this, so that we are able to limit the rise in the temperature. Also, you can see there are certain like graphs associated, like if we have some maximum power loss and how much is the ambient temperature allowable for a particular loss or the temperature. Also, if we have the what is the total power loss associated with the particular current that we want to flow in the device, you can see these things through the graphs. Also, now this was about the diodes. Now coming to the MOSFET, and you can see I'll briefly go through this similar in a similar fashion of the diodes, like you would have seen the characteristics of the MOSFETs as well. We have the forward blocking, we have the mainly three regions: forward blocking region, active region, and ohmic region. Usually we want our like device to operate in the ohmic region, because like it will follow the Ohm's law, like in the forward blocking, what happens is like the gate threshold VGT VGS voltage is not provided, like our device is not able to conduct in this region. And if we give a certain amount of VGS above the threshold, then our device can go into the ohmic region, and in this region we know that it will follow. We have a this is a linear region, and our DS on will follow the ohmic law. Usually for our MOSFETs we operate our devices in this ohmic region. And for the like similar to in this, like if you can see the transfer characteristics, we can also have for a MOSFET, which is the like graph between the VGS and ID. It will follow like up to a certain VGS, no current will flow through the drain source, but after some V threshold, our current will start rising, and these are known as the transfer characteristics of this MOSFET. And also you can see from this we can get the forward transfer conductance, which is the ratio of the like VGS by ID, like similar to what we found ODS on. Coming to this, like now we can see the switching characteristics of the MOSFET here as well. So if you can see here, our top, it is the gate source voltage, and now what is happening is earlier our switch is in the blocking volt. Now what we want to turn on our devices. So before that, there is our device is blocking some voltage VDS. Now what will happen, we will give because like we know our MOSFET is a control device, and it won't turn on until like we provide the gate source voltage across. This is a voltage control device. So as soon as we apply the voltage, initially there won't be any change up till the threshold voltage. As soon as like my VGS voltage reaches the threshold voltage, my current will start to rise. As you can see, as soon as my voltage goes to the threshold voltage, current rises up to the, and also my VGS starts to rise, and current VGS will rise up to the till my like current goes to the peak value. After that, what happens is my VGS voltage remains constant for some time. This is known as the Miller voltage or Miller plateau. So what will happen is like as we know, like there will be some oscillations because of the parasitics as well as the forward recovery. At this stage, like after this, the current reaches the peak value. What happens is like my voltage will start to fall. Now my voltage will fall up to like you can see up to around like this point. This is known as like a TFV, where my voltage falls. Like uh, the time from this where my VGS goes to 0 to VTH is known as the delay time, TD on, turn on delay time. And after that there is TRI, this is the rise time, and there is then time after which the voltage will start to fall up to like 90% of it. And then after this, that voltage goes to the zero, and my gate source voltage will further rise, and after that it will stay there, and my current at that time will be in the steady state value. That is my turn on process. Now similar thing will what will happen during the turn off. So what will happen during the turn off time, as soon as like before that my device will be carrying the steady state current. Now my VGS voltage will start to dip. As soon as my voltage will there will be a small like rise in the VDS voltage, but as my VGS voltage will hit the Miller plateau, my like voltage will begin to rise and shall block like the full VDS voltage. As soon as it will reach the full VDS voltage, now my current will start to drop. Now my current will fall and my VGS voltage will reach to the threshold voltage. During this voltage from Miller plateau to the threshold voltage, my current will fall, and this is the current fall time. Fall in the TFI is fall in the current time, and after that my current will go to zero, and my voltage will be around like the steady state VDS voltage. This was about like the turn on and turn off characteristics of the MOSFET, and you can go through the detail of it, like what is actually happening, the device, the physics of it. You can go through the lectures as well as you can see, you can search for this and go in the detail how the turn on and turn off happens of this MOSFET. And usually you can see for the MOSFETs like in the data sheets a number of terms are present in this, like If you can start, the first thing it is like voltage and current ratings will be given, the parameters. If you can see, drain to source, like breakdown voltage, what is the minimum typical, it will be like around, it is given here for this type, for this MOSFET it is given like 200 volt. So it shall be able to like block a voltage of VDS of around like 200 volts. So continuous, also similar to this on the diode, there will be a rating provided with this continuous and pulse drain current. You can have a continuous current of at VGS 10 volt, like at 25 degree, that is 94 amps. At 100 degrees it will be around, like for the same thing it will be around 66 amps only. So you can see the continuous current rating decreases with the increase in the temperature. So we have to keep that in mind, like while going through the data sheet, what are our applications, for what particular application we want these devices, and is it satisfying our thing. Similarly, it will be giving you drain source on resistance will be given here, and other aspects like what is my gate source voltage needed, what is the maximum gate source voltage there, what is the threshold. You can see the VGS, it is given like plus minus 30 volt. There is a variation here around these are the range of the voltages you can see around which like my device will work. Also you can see what is the like losses associated with this power dissipation. You can see also you will be having a certain graphs, like we'll be having a junction temperature and RDS on. Also, if you can have, we'll be having a graph of VDS, drain to source voltage, and ID current for certain VGS voltages. You can see like 5 volt. If you can see, when we increase in the voltage, then there is not much of a difference in the drain current. You can see from 5 to top to the 15. And these are like for a particular applications, you can go through the data sheet and see your requirements and see if that thing we'll see in the problem solving, how to look for these thing, and will that satisfy our application and what we want for our specifications. Other things what is given in the MOSFET data sheet is like a gate charge associated, like in the switching when we turn on the devices. You can see these things, what is the like forward conductance that I had already discussed previously. Here it is giving like the 30 for a particular voltage of VDS of 50, and this thing, what is the total gate charge required to turn on the devices, that is given. Like if you can see, we have for the MOSFET we have the 3 terminals, gate, drain, source, and there will be like all between these terminals there will be some capacitances associated with it, and they are usually like gate source capacitance, gate drain capacitance, and drain source capacitance. But usually what is given in the data sheet is not like VGS, VGD. It will be given CISS, like input capacitance, and that is given by the sum of like VGD plus VGS. Output capacitance is given, that is the sum of VGD and VGS. There is a total of that. Here you can see 1070 for a particular conditions. Here it is given, and there is reverse transfer capacitance that is given by CGD, and there will be some value that will be there in the data sheet. Also there will be some it will be given like the total charge will be having if you can see the graph here, VGS, gate source voltage, what is the total charge turn on the device, will be having the turn on time. Then there this flat portion will be the Miller portion, and then after that we'll be having VDS. For different VDSs, what will be the peak charge to turn on that thing devices. Also you can see with the capacitances that have been provided here, if you take a look at this graph, VDS versus this capacitance, you can see as with the increase in the VDS voltages, there is a dip in the capacitance. That means our capacitance, these capacitance won't remain the constant, like the value of these capacitors are not constant, and these will change as with the different VDS voltages. If you can see, CISS more or less remains constant, but COSS and CRSS decreases with the increases like drain source voltage. Similarly for like this diodes, it will a certain data will be provided in the data sheet, like the forward current. You can see what is the current that it can flow, the pulsed current that it can carry, what is the voltage, forward voltage drop across the diode, what is its reverse recovery time, reverse recovery charge. These data will be like, if you can take a look at this, these are all given in the data sheet. Also, with respect to the thermal characteristics, you can have the thermal data as well, like what is the junction. If you want to like calculate the, if you have the total power loss, if you know the total power loss and you want to see the temperature rise at different junctions, you can calculate that if you know these resistance, and more usually they are also provided in the data sheets. Now this was about like what had been taught in the week. Now we shall like we can take a break of like 5 minutes here, like we shall start from 4:27. I think we will start 4:27. We shall start, we'll take a 5 minutes break, and then we can see look into the problem solving, and we can see if we want to choose a particular uh, components, how to do that thing. Is my screen visible? Screen is visible. Can anyone reply? Okay. So coming to the problem solving thing, as also like there will be like there will be a assignment given to you. It will be a data sheet that will be given of some component or part, and you have to like answer the certain questions that we'll be getting from this data sheet. So the question is like, study the data sheet of the MOSFET that has been given. The part number is given here, IRF 740 APBF, and answer the following questions. So you don't have to do, you just have to search this component, or maybe in the assignment it has been provided with you. If you search this component, you will get a data sheet. Download that data sheet, and by just reading that uh, thing, like you should be able to answer each and every question. Like here we will see how to answer those questions. Like first is the, what is the voltage rating of this MOSFET? So if you can see, like there will be some data that will be provided here, like if you can when you go through the data sheet of a particular component, you will be showing, there will be shown like VDS voltage. This VDS voltage is the amount of the voltage that our device will able to block, like will be able to handle or block this amount of the voltage. This is the voltage rating of our device. If you can see here, it is like 400 volts, and that is the answer to the question. Other question that is giving the voltage that is provided is the gate source voltage. This is the voltage that we have to give in order to turn on the device. Like this is the VGS voltage across the gate and source that we have to give in, like, for our device can get turned on. So but what is the voltage rating of our devices? That will be given by the drain source voltage that our devices will be able to handle in when it is in the when it is turned off. So here the answer to this question is, like, you can see for any other component or part that has been provided to you, like you can see this, what is the voltage, and you can answer that question. The second question is study the same data sheet. We have to like answer like continuous current rating at 100 degrees centigrade. What is the continuous current rating, and what is the pulse rate? We saw like in our uh, previous slides, like there will be two ratings. One will be like continuous, one will be pulse, one will be like non-repetitive. Like before the repetitive, it will be able to withstand, but some non-repetitive pulse current rating will be also there. So if you can go through that thing, like something like this will be data will be provided there. It is like you can see the drain source, it is provided is 400 volt, gate source is like plus minus 30. We can give it in between this, and you can see the continuous drain current. If we have a VGS of 10 volt, that means when we have a VGS of 10 volt and TC's case temperature is like 25 degree, then our drain current peak is limit is like 10 amps. But it is asking here at 100. So if you can see, there is other rating is provided at the 100 degrees centigrade. It is around like 6.3 amps here. You can like, so answer to this question is 6.3 amps. You can see that thing as well as like verify this thing from the graph as well. If you can see at the 100 degree, if you can see the arrow there where I'm pointing, if you can see the current at that time is like a little bit above like 6, to be exact it will be that 6.3 amps that is given here. Also if you can see, it is given that the pulse drain current is like IDM, like that is given. It is that this data is already provided in the data sheet, like you just have to look for it. Like it will be around, it is around like 40 amps. That is the answer to this question. So The fourth question, that is like for this device you have to see the on state resistance, and also it is given the test conditions is given VGS should be 10 volt and I drain current matlab drain current from drain to source should be like 6 amps. So if you can see, we'll once again go through this the data sheet, and if you can see here at the bottom, then it is given like drain source on resistance RDS on for the test conditions are provided here, like 10 volts and drain current of 6 amps. So these satisfy our test conditions, and it is given, it is the maximum RDS on, it will be around like 0.55 ohms. That is the answer to this question. But if it does not satisfy, our test conditions are not the same in the question, that we have to go to the graph and see for the particular test conditions, like from the graph, then we can calculate the RDS on. If we know RDS on, we know we have the ratio of like VDS to like I drain current, like then from that you can calculate this RDS on, like we saw how to do the ratio of that thing. Yeah, you can look into this the variation with the for a particular VGS voltage, you can calculate at that time. That is about the question number 4. Now coming to the question number 5, what is the maximum gate to source threshold voltage? That means like what is the maximum gate to source threshold voltage that we can apply without like damaging this. So here you can see there are like an n number of things. Drain to source voltage breakdown VDS, it is given like it has like 400 volt. Then temperature coefficient delta VDS कितना है वो भी दिया है. And then we have gate to source threshold. Gate to source threshold, like it is giving if VDS is equal to VGS and ID is like this. So minimum VGS gate to threshold voltage is like 2 volts and maximum it is around 4 volt. So it is asked in the question itself, like what is the maximum gate to source threshold voltage. Gate to source threshold voltage is given here, and you can the maximum value of it is like 4 volt. So the answer to this question is 4 volt. You don't have to do anything, just study the data sheet and the questions that will be asked, you will get an answer to them from our data sheet only. But you should be able to understand what we want, what is the need, and what we have to look for. That is the only thing that we have to see. Now it is like study the data sheet and calculate the total gate charge. We saw like it is a like to charge turn on the devices, we will be having the in the turn on time, then during the Miller time, and then here you can see from the graph this will be during the turn on, this will be during Miller, and then the total turn on time. If you can see here itself in the data sheet, it will be provided the total gate charge. This is given at these test conditions of like 10 volt, and if we have an ID of drain current of like this, it is around 36 nanocoulombs that is required, and that is the answer to this question. And if you have gate source charge in that will be like 9.9 coulombs, and gate drain charge will be GD will be to charge like that capacitance, that will be equal to 60 nanocoulombs. So the answer to this question will be 36 nanocoulombs. So this is the answer to this question, but these are very simple questions, but you should be able to know if we have to design a particular converter for a particular applications and so on and so forth, how to what are the parameters we have to look for, does a particular component suit our parameters and all. Question number 7, what is the typical turn on time in the nanoseconds we have to do? and we saw the turn on characteristics, and it comprised of like first like that delay time, then there was a rise time, and after that there was the time during which the voltage would fall. And so here it is giving turn on delay time, so is here giving, that is 10, then rise time is given, that is 35. And if we just here the other time is not given, like the fall, because like uh, if you can see that has been neglected here, and our turn on time will be equal to turn on delay time and rise time before, because after that our device will start conducting, because the current after this rise time our current will start conducting. We can say our current is in the conduction, our device is conducting. So it will be the sum of these 35 and 10, that will be equal to 45 nanoseconds. That will be the answer to this question. So after that, it is what is given is like turn off time is given, and also the fall time during which that uh, current will go to 0, that is to 22 nanoseconds, that is given. But here it is asking only about the turn on time, so we have to add up these turn on delay time and rise time. That will be 35 plus 10, that is the total turn on time that our device would take to turn on, that will be 45 nanoseconds. But these conditions will be valid for these things like RG on, but our gate resistance should be 10 ohms, RD, and these things, because we know like you will subsequently see during the gate driver design of this, if we change the gate driver resistance as well, like our turn on time will change, that you will subsequently see. These conditions are true only when these things will satisfy, these test conditions will satisfy, then only our turn on time will be around 45 nanoseconds. For different parameters our turn on time will change, then we have to accordingly calculate from the graphs and the data provided by the company. So and then we have to see for different gate driver gate time resistance what is the turn on time and all for that thing. So we have to see what are the test conditions here, and for these test conditions this holds true. Number 8, we have to calculate the input capacitances. So we know that CISS is the input capacitance, we know, and it will be equal to CGS and CGD. So the value of it is like given, the typical value it is here given is in the picofarad, and here you can see it is 10030, and you can see here that is given. Also you can see the other parameters here, and also like I already told you, like the value of these capacitances change at different voltages, so we have to see for the test conditions that we have what is the VGS, what is the drain source voltage at that particular voltage, we have to see. Now if these parameters change, if you can see in the graph from 1 to like 1000 like 100, you can see a dip in the like CISS and COSS. So if for some other voltage it is given, then you have to accordingly calculate. Since it is given here only, so at this voltage you can see from the graph itself it is equal to 10030 volt. That is the answer. What is the maximum reverse recovery time of the body diodes? So we saw that maximum reverse recovery time will be equal to like TA plus TB, and here it is given the total reverse recovery time, body diode reverse recovery time, TRR, and these test conditions should these are valid only for these test conditions, like TJ equal to 25 degrees, my forward current should be 10 amps, and di by dt is 100 amps per second, then only this is true. If this if we have, if it is given like for different test conditions, then you have to calculate from the data given in the data sheets or graphs. You have to see what is the actual reverse recovery time of the diode. So here the answer is 360. When the question is straightforward, you can just straightforward say, and it is not like for other things you have to calculate, then you can look for that thing as well. Here it is 360. So these were about like, now in the question number 10, what is being asked is, this was about the question about the data sheets up to this. Now what is being asked is, for the question number 10, we have to design a boost. For designing a boost converter, a MOSFET and a diode need to be chosen such that the voltage rating is above for 75 volt and continuous current rating is about 10 amps. Which of the following MOSFET and diodes will you choose for the design? So in the question itself, two things are given. We should have a voltage rating above 75 and we should have a current rating above 10 amps. So these two test conditions we should satisfy, of 75 above 75 volt and 10 amps. You can see like in the options itself, like two MOSFETs are given. Like in A there is one MOSFET and in B there is one other MOSFET. Like two MOSFETs are given. Then you can see in C and D these MOSFETs repeat. And in a similar fashion you can see there are two diodes here, like A and B, and B and C are same and A and D are same. So here we have two things. We have two MOSFETs and we have two diodes. What we will do is, we will look for the data sheets of both of these devices. So we look for the data sheets of this two MOSFETs and two diodes. We'll see which of our devices will satisfy the conditions that are given in the question. First, coming to the MOSFET. These are the MOSFETs of like two MOSFET data sheets. What is the requirement is, voltage should be greater than 75 volts and current should be greater than 10 amps. If you look at the data sheet of the first MOSFET, you will see the drain source voltage limit is 50 volts. So this first MOSFET doesn't satisfy our voltage requirement of 75 volts. But you can see the continuous drain current is at 25 degrees 15. It can satisfy like our current requirement, but it is not satisfying our voltage requirement. So this is not the answer. This is not the device. Now if we look for the other devices, you can see the voltage is drain source voltage. It can block up to like 200. It is able to handle up to 200 volts. So first voltage rating, it's able to satisfy that thing. And now we'll look for the IC continuous current rating. If you see the continuous drain current rating, it is like at 25 degree it is 20 amps and at 100 degree it is 12 amps. Like it is able to satisfy this second condition as well. So we shall choose like this MOSFET, IRF P240PBF. So this is the MOSFET that we shall choose. Now we shall look for the diodes. So similar to the MOSFET, we have the two diodes. If you look through the data sheet of like the first, we have repetitive reverse voltage of like 300 volt. It is able to satisfy this voltage requirement, but it's not able to satisfy the current requirement of average current. At 150 it is around like 6 amps, but here our continuous current rating should be of around 10 amps. So first the diode doesn't satisfy our requirement, doesn't meet our requirement. So now we shall like move to other diode, LQA30T300. If you will see, peak repetitive reverse voltage that it is able to handle is 300 volt and our requirement is 75 volt only. That means this is able to meet our voltage requirement. Now we shall look for the current requirement. If you can see, the average current that is able to conduct is like at 150 degree and junction and case temperature of 99 degree is 30 amps. That also meets our requirement of 10 amps. So we shall choose the diode of LQA30T300. So and both of these like are satisfied in the option D. That means our option D is correct. So in this way you are able to like see now if we have a question, like if we have certain requirements, what to look for and how to like choose different components for our if our parameters or specifications are given. Now we have certain component list of the components. If we need to choose from them, then you can look into the data sheet, see if our requirements are being met by a particular component, and we can choose a best amongst them as well. If there are multiple, we can also choose a best amongst them. And this was about the questions today. Thank you everyone. And this was about the question. If any of you have any questions, and he or she can ask. If not, then we can close our meeting for today. Any questions? Any questions? So if there are not any questions, from the graph, can you show the capacitance? So if you can see here, like it is given CISS. Yeah, these PPTs will be shared uh, with everyone. The link will be shared by the NPTEL people, and you can look have this recording will also be saved, and this recording will also be shared with you as well as the PPT. So here you can see the input capacitance, CISS. If you can see, we have a three graphs: CISS, COSS, CRSS graphs, and there is a wide voltage range VDSS that is given. So here it is also given like VGS is 0. So it is VGS is 0, and frequency of 1 megahertz. It is given frequency of 1 megahertz. Now if you take a look, VDS of 25 volt. Where is VDS of 25? This is the logarithmic scale. So this is 1, this is 10, this is 100. So it will be somewhere here. It will be somewhere here. So if you can, it will be somewhere here. And if you will particularly see, like this graph is not exactly here, like our 10 raised power 3 is up to here. Then if you will see here exactly at the 25 volt, it will come around to be equal to like 10,030 picofarad. So you can see for different VDS voltages, and if you will open up the graph of any of the devices, it shall follow whatever is given in the data sheets, provided the test conditions at which the graph is taken are same that is given in the. This is the only graph to check the capacitance. This is the variation of the capacitance that is given. You can see what is the data that is being provided by the manufacturer, because these manufacturers will test on these devices and will provide the data with you can go through the data sheet and see in the graph sections what are. One more graph. Which one? This one. This is about the gate charge. This is not the capacitance. This is the gate charge. This is not the capacitance. This is the capacitance. This is the capacitance. Is it clear? So you can see like this is the VGS, this is the total gate charge for a particular like VGS. When you apply a certain VGS, what is the VDS you have to see at that thing. Like you have, it is given when VDS is 80, when VDS is 200, you have to follow this graph. When VDS is this, you have to follow this graph. And you have to see if your ID is around 10 amps, that means drain current is around this, then you can follow this graph. You can see if I am applying this amount of VGS, let us say of 10, this is 810, you can see what is the like total charge you can calculate at that particular point. Are you able to follow? So in a similar fashion, you can see there are different other graphs that are provided in the data sheet. It is what has been asked in the questions, and most probably, like, the questions that have been asked to you, you'll get an answer directly from the data that has been provided in the data sheet. And if not, there will be some graphs provided towards the end of the data sheet, and you can like correlate it from that. Whatever the data that is being provided, is it true, is it being followed from the data sheet? You can check that thing as well. Any other question? So if there are not any other questions, then we can close our session for today. Thank you, everyone. Thank you.